We'll continue to look at some of the details of the equilibrium constant presented in Chang's textbook section 14.2. I really suggest that you read this section and see the good examples that he has worked out. In this section, we want to examine what changes to the equilibrium constant when we make a change to the chemical reaction. So here's a simple chemical reaction of H2 and I2 combining to form hydrogen iodide, and the equilibrium constant is, of course, products over reactants. And now what I want to do is change this reaction. So if I take this reaction and divide each of the coefficients by 2, how does the equilibrium constant change? Well, the reaction then is, of course, 1/2 H2 plus 1/2 I2 forms a mole of HI, and now the equilibrium constant is different. HI is to the first power, and H2 and I2 are both raised to the 1/2. So clearly the relationship K for the first reaction is not equal to K for the second reaction, but they are related. So K2 does relate to K1, but in what way? Well, the difference between these two K values is K1, if I take the square root of that, or raise that to the 1/2, I'll be exactly the same as K2, and this is really important. Whatever math I perform to change the reaction, multiply by 1/2, I raise the K value to a power of 1/2. If I were to have multiplied this reaction by 3, then I would cube the value of K. One quick look at manipulation that we've seen before, but it's good to see a second time, is if I take a reaction, reactants go to products, and just switch the products and reactants, what happens to the K value? And so for this flipped reaction, the equilibrium constant expression is, of course, products over reactants, but how does K3 relate to K1? And K3 is the reciprocal of K1. Reaction products and reactants are flipped, the K value is related to its inverse. Okay, some new material to examine. In the thermochemistry chapter from first semester chemistry, we saw that chemical reactions can be added, that I can add reactions in order to produce a similar reaction. And in this example, given reactions can be added, and we will add these two reactions. And adding a chemical reaction means just write all the reactants for both reactions on the reactant side. Here are all the reactants. And write all of the products. Products are CO2. And now, if a component appears as both a reactant and as a product, they cancel. So the O2's cancel. And CO2, there are two CO2s on the reactant side and one CO2 on the product side, so those cancel, leaving only one CO2 on the reactant side. So adding these two given reactions gives the reaction that's at the top of the page. So the question is, how do the known K values, K prime and K double prime, combine to give the K value of the added reactions? Well, let's look at each of these three equilibrium constants. For the unknown reaction, the equilibrium constant would be, and so the equilibrium expression is CO squared over CO2, and you notice that we're not including the solid carbon as part of the reactants. Now let's look at the other two. The first known reaction is the concentration of CO2 over the concentration of O2, and the final one is the concentration of O2 times the concentration of CO squared over the concentration of CO2, of course raised to the second power. Now, can I combine K prime and K double prime in order to give the equilibrium constant K? And if you look at them, I'll do the math, but K will be equal to K prime times K double prime, and let's see how that works. K prime is CO2 over O2, and K double prime is the concentration of O2 times the concentration of CO squared over the concentration of CO2 squared. And we can see that in fact the exact same canceling that we were able to do in the summed reactions gets done again. There is an O2 in the denominator of an expression and an O2 in the numerator, and there are two CO2s, one in the numerator, and I get to cancel one of them in the denominator, and that leaves us with the equilibrium expression CO squared over CO2, which is exactly what the summed reaction equilibrium constant is. So it's always the case that when you add chemical reactions, their K values don't add, but rather they multiply together to give the equilibrium constant for the summed reaction. Now, let's practice that with a specific problem of known K values. Here's an important atmospheric reaction of SO2 turning into being oxidized to SO3, and we don't know what that equilibrium constant is, but the equilibrium constant for two similar reactions is in fact known. In this case, I can't just add the two given reactions. That doesn't give the desired reaction. The desired reaction has two SO2 as a reactant, and SO2 only appears in the first reaction, but it appears as a product. And so I'm going to have to flip the reaction and multiply by 2. So I'm taking the first known reaction, multiplying everything by 2, and flipping reactants and products to yield and now the value of the equilibrium constant, because we flipped the reaction, will be 1 over the initial reaction, and because we multiplied by everything by 2, it will have to be squared, and that gives 3.5 times 10 to the minus 75. Now the second reaction is the one that gives us SO3. SO3 only appears in the second reaction, but this time it appears as a product and with the coefficient that we need for the reaction we're trying to determine K for. So that one is just a repeat, and the K value is unaltered, 8.8 times 10 to the 95, and we can sum our two reactions. In this case, O2 appears as a product and 3 O2 appear as a reactant, so I can cancel 2 of those, and 2 sulfurs as products and 2 sulfurs as reactants, and we're left with 2. And now the K values, value of K, will just be the multiplication of the two K values, so 3.5 times 10 to the minus 75 for the second K value, and K for our reaction is 3.0 times 10 to the 21. And so you can see that sulfur trioxide is heavily favored when oxygen is present with SO2. So often you'll need a K value for a reaction for which you can't look up the K value, but similar chemical reactions, the K values are known and they can be combined by multiplying K values when the chemical reactions are additive. The last topic that needs to slip in one place is a term called percent dissociation. It's a commonly used term, and the meaning of percent dissociation is fairly simple: how much falls apart, and mathematically that is the amount that falls apart in units of atmospheres or molarity divided by the initial amount of the reactant. So in this case of PCl5 dissociating, so in solving an equilibrium problem, we create the equilibrium table, and X often represents the amount of reactant that has fallen apart, and so percent dissociation can be given in terms of that variable from the equilibrium table, X. In this example, the percent dissociation of PCl5 would be given as the initial amount of PCl5 in molarity, and X represents the amount that falls apart, and then of course if you want it to be a percent you need to multiply by 100%. Sometimes, however, X does not represent how much falls apart. In this case of NOBr2 dissociation, the amount of NOBr2 that falls apart would be given as 2x, and so the percent dissociation of NOBr2 is 2x. This is common, and you'll probably see this term percent dissociation in several of the homework problems, and so you might hear that percent dissociation of PCl5 was 17%, so 0.17, and if the initial amount of PCl5 were 0.025 molar, 0.25, we would be able to solve if the initial amount of PCl5 were 0.25 molar. We could solve for the amount of X in the equilibrium table, and X would be equal to 0.043 molar. So percent dissociation is a term that you'll be comfortable using with a few of the homework problems.